Okay, so good afternoon. Let's start. First of all, we're gonna have a warm-up problem, and this is matrix A. It's a 3 by 2 matrix, and B is 0, 0, 1. Okay, so it's a length 3 vector. So you can try to solve Ax equals to B, and you'll find that there's no solution. So we want to do the least square solution, where, as we briefly talked about last time, but we're going to talk in more detail today. So we first compute the projection of B to the column space of A, and then we obtain the least squares solution by solving this modified problem, not as Ax equals to B, but Ax equals to B hat. So let's solve this problem. So how do we compute? So first of all, we want to make sure that we've already got an orthonormal basis, or at least an orthogonal basis of the column space of A. We find that the column vectors are indeed orthogonal to each other. The inner product is 0, so we're good to start. So we compute B hat, and this is, so first we have the first vector, so A1 times A1 dot B is a very mechanical procedure, divided by the norm of A1 squared. And then we have the second part, which is A2, and again we have a number, A2 dot B, divided by A2 squared. So how do we compute? We just literally just do the dot. The first one is 1, 0, 1. A1 dot B is -1, so this is -1. A1 squared, 1 plus 1 is 2. And then we have this one, but you see A2 dot B, and this is 0 because it's the orthogonal. So I just directly put a 0 vector here. And this is -1/2, 0 minus 1/2. Any question? Okay, now we have identified this vector B hat. Now let's solve Ax equals to B. So this is the Euro thing, 0, 0, 0, 1, 0, -1, 0, minus 1/2. And we can directly obtain a solution. We found that the solution is nothing but -1/2, 0. And as we talked about last time, this is our least squares solution. We haven't fully justified why this is the case, but I've already talked about the procedure. Even though the original problem, when you put 0, 0, 1 was not solvable, but this becomes a solvable problem. Any question? Okay, so now the first topic today is to justify why the procedure above gives us the solutions to the least squares problem. Honestly, if you have a lot of vectors in the column space of A, this procedure is pretty annoying. There's actually a simpler approach, so we're going to also talk about. The first thing we're going to say is to state again the best approximation theorem and prove that. So W, let me say again, so W in Rn is a subspace. V is any given vector. Then we can always decompose V into the addition of two vectors where W is in the subspace and Z is in the W perp. Here, due to the uniqueness theorem, W is the projection of V onto W. And we know that Z, the length of Z, is measured by V minus W, by the definition here, is smaller than or equal to the length of V minus W prime for any W prime in W. So as we talked last time, the idea is rather intuitive if you look at it from the geometric perspective. This is the origin, and I have a vector V. This is a projection for the W. This is the orthogonal vector, and this is called the Z. Now, if I pick any extra W prime, and we can still measure the distance, which is V minus W prime, because there's an extra vector here. By Pythagoras theorem, the length of the Z will be less than or equal to the length of this Z prime. And that's literally the idea. And the proof is almost exactly like that, which is I now take any W prime in the subspace W, and we compute the length V minus W prime squared. And I can write it to be two things. One is V minus W, the other is W minus W prime, right? I can feel free to put a parenthesis there. So this is literally an equality. Now we see that V minus W is just a Z, which lives in W per. W minus W prime is a linear combination of vectors in W, and therefore this is in W. Again, by Pythagoras theorem, and this is Z squared plus W minus W prime squared. This one is a non-negative number squared. And now we just cancel the square on the left and right hand side. We proved the theorem. So literally says why W prime, this length of the Z prime is bigger than or equal to the length of Z. And therefore, this is the best approximation where this vector Z measures the difference between V and is a best approximation. You can view this Z as a residual. And the best approximation theorem says that the residual is minimized. Any question? Now, let me use the best approximation theorem and try to solve the least squares problem. So our starting point is that AX equals to B has no solution. There's nothing we can do about that. But we can, let's say, for concreteness, A is m by n, B is in Rm. So the solution is in Rn. So, but we can always ask whether we can find a least squares problem so that the smallest amount of prime is being made. What it means is that I want to find x hat so that the difference between ax hat and b is smaller than or equal to ax minus b for any x in Rn. And you can see that this is nothing but to say I want to minimize x such that ax minus b squared is as small as possible. So these two formulations are completely equivalent. Now I can use best approximation theorem for W equal to the column space of A, because A times X is just trying to explore all the possibilities in the column space of A. And I immediately have A times X hat should be equal to the projection of B to the column space of A. Any question? Let me explain again. This one is trying to look for all the possibilities within the column space of A. We want to minimize that. So B becomes this V. These are the column space of A. I want to find a vector in the column space of A that is as close to B as possible, which means the residual should be as small as possible, and therefore that is the projection of B to the column space of A, as we have done at the beginning in the warm-up problem. So this immediately gives us an algorithm. That is, I take this vector B and I compute the projection. If I already have orthogonal basis for column space of A, I compute n inner product. And then I use this and solve the linear system. That's definitely a doable thing.
Why you're using only column A?
The column, because A times X is in the column space of A. So you're linearly combining the columns.
Oh, okay.
Any other question? So let's say there is a simplified solution. The simplified solution is the following. Again, from best approximation theorem, we find that B minus AX, this one should belong to the column space A perp, right? So let me draw it here again. So this is B, and this is the projection, which is AX. So the difference here belongs to column space A perp. But what was the column space of A perp? We discussed that last time. This is the null space of A transpose. Why it is null space of A transpose? Because everything that is in the column space of A perp satisfies A transpose X equal to 0. That is literally, you say, inner product with the first column is 0, inner product with the second column is 0, blah, 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 blah. And so that just says A transpose X equal to 0. Now, if it belongs to the null space of A transpose, what does it mean? It means that A transpose B minus A hat, this one should be 0, right? This is what it means that B minus AX hat is in the null space of A transpose. And now I just rearrange this equation a little bit. I found this problem. On the left-hand side, I have A transpose AX hat. On the right-hand side, there's new right-hand side, A transpose A. So this one should also give me the solution to the least squares problem. And this equation, called the normal equation. So this problem is actually a lot easier to solve if you think about that, because this says, well, ax equals to b may not have a solution. Let's say this A may have, I have 10,000 data points, recall the linear regression problem. So I have 10,000 data points, I have two numbers to determine. So A is a matrix of size 10,000 by 2. By computing A transpose A, I obtain a modified matrix, which is of size 2 by 2. The right-hand side, originally there were 10,000 data points, so it's a vector of size 10,000 by 1. Now I compute A transpose B, now it becomes, the number of right-hand sides becomes 2, right? So this can be a much smaller problem than the original one. Any question? Okay, so let us now go back to the warm-up problem. So we use the one way to solve it, which is this. Now, what I would like to do is to solve, compute A transpose A and compute A transpose B, so that to confirm that we get the same solution, which is x hat to be minus 1, 0. It's a very simple procedure. So I just compute A transpose A. So this is the transpose of that. 1, 0, 1, 0, 1, 0. So this is 2, and this is orthogonal, 1. A transpose B is the same transpose matrix times 0, 0, minus 1. And this is minus 1, and this is 0. Now I solve the simpler problem, minus 1, 0. This problem is guaranteed to have a solution. Why guaranteed to have a solution? Because I'm asking for the solution that is, makes the least amount of crime. So I just to put, let's say, x equals 0, it would make a finite amount of crime. So when I minimize, the minimizer must exist. So this one is, the solution is x hat. So you can see this is already in the low echelon form. I'll give you exactly the same solution. Any question? So long story short, we started from the problem of least squares. The beginning, it sounds like this is a really complicated optimization problem. And we introduced the concept of the orthogonal subspace. And we can find that, give me a subspace, I can decompose any vector into a component in the subspace and the component in the perp. And this decomposition is unique. And we used this associated best approximation theorem and solved the least square that provides a general and really simple solution. If you look at my Python code, last time when I presented to solve, to predict the COVID-19 cases, now you should be able to understand that code, assuming you understand how Python and NumPy works. What I literally did was to download the data from CDC and form a matrix A. You can easily see why AX equals to B has no solution. I computed A transpose A has 2 parameters, a matrix of dimension 2. I computed A transpose B, I just solve it, and that's it. So the second topic I want to talk about is how to generate, give you a subspace. How do I generate a basis of it? You say, wait a minute, we have learned that in chapter 4, you give me a subspace, give me, it is span on something. I do know how to generate a basis. But now we see that if you have an orthogonal basis, it really makes a lot of calculations easier. So what I now want to find is not only to find a basis, but actually to find an orthogonal basis. Find an orthogonal basis of some subspace. So let's start with an example. So W is 110, W1 is 110, W2 is 111, and I have W is given by, so the span, we've talked about this before, but let's just do it again. So W is the span of this. I want to construct an orthogonal basis. How do I do that? So, I mean, the first vector, let's say this basis, let me give it a name, which is called the W1 tilde, W2 tilde. So the W1 tilde, I mean, the first vector, I only asked it to be orthogonal, so I can just take it to be say, W1. And W2, we find that, I mean, the inner product is not zero, so they're not orthogonal, but I can project away the components of W1 in W2, which means that I compute W2 minus the projection of W2 on the span of W1 tilde, which is the same as W1, right? Because so this is W1, this is W2. What I want is to project away this component that's in W1, and I only want to find the new orthogonal contribution, which is W2 tilde. So we know how to solve this. So W2 is 111 minus its projection. So let me write it down. So this is W2 times W1, 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 W1. And you can just evaluate, and this is a 0, 0, 1. So you get rid of the component of W1, and the remaining part is orthogonal to that. And now we find an orthogonal basis, which is W1 tilde, W2 tilde. Now you say, what if I have 3 vectors? What if I have 4 vectors, so on and so forth? So the idea is that this is really similar and goes under the name of the Gram-Schmidt process. So what is the Gram-Schmidt process? It says, if I start from a set of vectors, V1 to Vk, is a basis of some subspace, let's say H. H is a subspace. Now subspace of H of Rn. So now I want to find an orthogonal basis. Once I have identified an orthogonal basis, turning that into an orthonormal basis is really simple because I just need to normalize it. And let's say call it W1 to Wk. What should I do? It's a very simple procedure. The first vector W1, I can just take it to be V1. There's no problem with that. And now I define a subspace capital W1 to be the span of W1. Okay. Now W2, I take V2 minus the projection of itself on W1. I get rid of the contribution from the subspace I've already defined. And then this one, by definition, W2 is orthogonal to W1, or W2 belongs to W1 perp. Now I define new subspace, defined to be W1, W2 is a span. Now you see where this is going. Now you have a third vector. I minus the projection of V3 on W2. Therefore, W3 is in the W2 perp, and therefore in W1 perp. Now W3 is in the span W1, W2, W3, and now I can just keep going on until WK is VK minus the projection of VK onto WK minus 1. And that's it. Any question? So this is the well-known Gram-Schmidt process for generating an orthogonal basis. You start from any basis and just apply this Gram-Schmidt procedure, and you will be able to generate an orthogonal basis. Let's take a look at the example. So let's say we find an orthogonal basis for the solution set of the following equation: x1 plus 2x2 plus x3 plus 2x4 equals to 0. So I have 4 variables and I only have one equation. So almost guaranteed that I'll have infinite number of solutions. So the augmented matrix is really 1, 2, 1, 2, that's 0. Now, how do I do? Solve this problem. 1, find the basis. So this problem is really a chapter 1 to chapter 4 problem. I won't repeat. You can do that as an exercise. So there are 3 free variables. So I need to find 3 things. One is a -2, 1, 0, 0. You can check -2, 1. And the second is a -1, 0, 1, 0. V3 is -2, 0, 0, 1. Okay, so I just find a basis. So let's say we start from this one, and you can just check that they indeed satisfy the equation. Now is to find orthogonalize the basis. And using the Gram-Schmidt procedure. Let's just carry it out. The first one is just the V1, -2, 1, 0, 0. The second one is V2, minus the projection of V2 on W1. So let me directly write down V2 dot W1, W1 dot W1, W1. So V2 is minus 1, 0, 1, 0, minus V2 times W1. So this one is 2. Okay, so I have a 2 here. And W1 times W1 is minus 2 times minus 2 is 4, plus 1 is 5. And W1 minus 2, 1, 0, 0. So this is equal to minus 1 plus 4 over 5. This is a minus 1 over 5. This is just a minus 2 over 5. This is nothing's here, 1, 0. And you can easily check W2 is indeed orthogonal to W1. Any question? Okay, so seems like you're now pretty familiar with this procedure. We'll just carry on. So this should be V3 minus the projection of V3 to the span of W1 and W2. I just W1, W1, this is a number times a vector, minus V3 times W2, W2, W2 times W2. You just carry this procedure as a bit boring, and I just write down the answer, minus 1/3, minus 2/3, minus 1/3, 1. And you can verify as an exercise that this indeed spans the same subspace, and these are orthonormal. Good?
Why were minus W1 and W2? Why were both
Projection.
minus?
So these are the projection. Projecting V3 to W2, capital W2 is the span of W1 and W2.
Oh, okay. Thank you.
Okay. So basically through this exercise, we found the line of best fit, essentially.
Oh, no. There's no best fit whatsoever. This is just to generate an orthogonal basis. So because in order to do some projection later, and you have seen that if you have an orthogonal basis, it's a lot more convenient. And just a Gram-Schmidt process says, given any basis, how do you turn that into an orthogonal basis? Does that answer the question?
Oh yeah, thank you.
Yeah. Okay, so now let's look at this Gram-Schmidt procedure a little bit further, and I'm gonna introduce a very much related topic, which is called the QR decomposition. The QR decomposition is really nothing but rewriting the Gram-Schmidt. Okay, what do I mean? So let's say I start from a matrix A given by 3 columns, V1, V2, V3. Now I apply the Gram-Schmidt. How does it look like? Let me write again. We have seen that just 3 times. W1 equal to V1. W2 equal to V2 minus something I don't care, W1. It's not like I don't care, but it's a number, okay, times W1. W3 equal to V3 minus a number, W1, minus another number, W2. And we can continue, but I'm only using matrix with the 3 columns as an example. Everyone following what I'm doing here? Good. So let me rewrite this. I want to write A equal to something. A is V1, V2, V3. So let me rewrite. So rewrite this to be A is V1, V2, V3. I just move all these stars, which I don't care, they're just a number, and the associated with W to the left-hand side. So this is, it's a four linear combinations of W1, W2, W3, which is an orthogonal basis. The pattern is as follows. V1 is just equal to W1. Therefore, these two are 0. V2 equals to 1 times W2 star times W1. I don't care what this number is, but it doesn't depend on W3. Therefore, this is 0. Similarly, for A3, I put a 1 here, I have this a star and a star. Any question? I'm doing nothing.
Professor, the stars here can be different from each other, right?
Of course, yeah. Just
Would
the number that I don't care.
In the matrix, would the stars be negative since above their minus star?
Yeah, so minus star means that when I move to the left-hand side, it becomes a positive star. But the minus sign, even the minus sign doesn't matter. It's just a number.
Why? Can you explain why this is 0 again?
0 because it has no dependence. V1 equals to W1. Let's look at this. V1 equals to W1 times 1 plus 0 times W2 plus 0 times W3 so that it is W1. Right? So that's why there are zeros here. Similarly, V2 doesn't depend on W3 and therefore there's a 0 here.
Oh, okay. Thank you.
Okay. So I'm doing nothing but other than rewriting the Gram-Schmidt procedure into A equal to something. However, two things emerged. One is this one is a matrix, this matrix of orthogonal column vectors. This is a matrix of orthogonal column vectors. And therefore, I can call it a Q. This one is an upper triangular. Okay. This is the upper triangular matrix. Okay. So, so I've decomposed A into the product of two things. One is a matrix whose columns are orthogonal. The other is upper triangular, as you can see, of which the diagonals are 1. So because any basis can be orthogonalized in such a way, so any matrix would have this so-called, such a form of the decomposition. So what is the QR factorization? QR is just a small modification of this thing. I want to convert the orthogonal columns into orthonormal columns. To do that, I only need to divide by its norm, by its length. But these numbers needs to be compensated somewhere. To compensate this, you can easily find that I can just put this to the diagonals so that this one multiplies that, W1, W1 cancels. This one, this becomes some different stars. So, but again, I don't care what these are. So the important thing is W2 divided by its length times its length equal to W2, and similar thing for the W3. So now this is a matrix with orthonormal columns, often called a Q. We're going to talk about that later. And this remains to be upper triangular, and it's called R. So we have A equals to Q times R, and this is called the QR decomposition. That's why it is nothing but another way of writing the Gram-Schmidt process. The QR decomposition is a very, very important technique in the field called the numerical linear algebra. When you do calculations on the computer, but those things I'll leave it to you. If you want to take 128 A or B, you'll have a more detailed understanding of that. Any question?
I have a quick question.
Yeah.
So if you scroll up a little bit, where you first had your first stars, I think they were green. Yes, these stars. These are supposed to represent like the dot products between V1, U1, etc.
That's right.
So when you scroll down a little bit, when you have your initial two matrix upper triangular one,
Right.
these stars, does it matter which one of the above stars you have, or can they be any order, any random?
No. This corresponds to these stars. I mean, if you want me to label them, this is star 1, star 2, star 3, and this should be star 1, star 2, star 3.
In that order, right?
Yeah.
Okay.
Just
wanted to clarify.
And you will find where they are. It's just to say I
Sure.
write stars there just means I don't care where they are. I only care about the structure, which is there's one orthogonal matrix and the other one is upper triangle.
Okay. Thank you.
Okay. So from here, you have seen for the first time, I've talked about a matrix of which the columns are all orthogonal. So let me talk about things in a more formal manner, which is I define something called orthogonal matrix. Portion. This is very confusing terminology. The reason why it is confusing is not because of orthogonal, but really an orthogonal matrix, after I define it, you'll find that it's better to just call it orthonormal matrix, but somehow the name just stays in the literature called orthogonal matrix. So an orthogonal matrix is an n by n square matrix. One, it's an n by n. Second is U transpose U is the identity. And then it is called orthogonal matrix. So what does it mean? Why do I call it orthogonal matrix? It's because if I consider the n columns of U, and now I look at this U transpose U and see how can I write it down explicitly for each component. The first one is U1 transpose U1, but we know that we can write it as U1 dot U1, the inner product. Similarly, the 1nth entry should be U1 dot UN. The n1th entry should be UN dot U1. This is UN dot UN. So it's an n by n matrix. If this is identity, what it means is that the length of each vector on the diagonal, there are 1. And ui.uj is 0 if I is not equal to j, which means that ui is orthogonal to uj. So now you see why I call it confusing terminology, because if I were just saying that this is a diagonal matrix, then it's an orthogonal matrix without any problem. But turns out that this is not only an orthogonal basis of Rn, but it's actually orthonormal. There's also a normalization condition here. So in other words, u1 to un is an orthonormal basis of Rn. So, okay, so this is the first thing. The second thing is, why do we want to consider orthogonal matrix? The reason is its inverse. One advantage is its inverse is really, really easy to compute. Let's recall, how do we define the inverse? So inverse is like if there exists a matrix C such that multiply them is identity, I can call this one A inverse. Now you see, this is exactly of the same form. Therefore, for any orthogonal matrix, U inverse is just its transpose. This is really easy because computing the inverse requires normally solving n linear systems, but the transpose is just a transpose. And this one says if it is orthogonal matrix, then its inverse is nothing but its transpose. That's the first thing. The second thing about the orthogonal matrix, which is not so obvious if you think about that, is if A inverse times A is identity, we also have A times A inverse is identity. I mean, that seems to be so natural. Applying this to the orthogonal matrix, what we have is U transpose equal to identity n, because this is its inverse, right? But what does U times U transpose equal to identity mean? I start from U1 to Un, I give you the column vectors. I can also write them in terms of the row vectors, called the W1 transpose, Wn transpose, so that each of them, they're like a row. So these are row vectors. So maybe 2 pages. So here we have U times U transpose equal to identity. This means W1 transpose, Wn transpose times W1 to Wn, this is identity. And therefore, you can write it in the same way as we had before. This is W1 dot W1, W1 dot Wn. This is Wn, 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 W1 equal to identity. So it says the row vectors are also orthonormal. It's really not that obvious because it says you give me there are n column vectors, right? Defining this particular way, you have an inner product, and these are orthonormal. And I just take a look at the row vectors. Usually, these two things are not related to each other at all. But due to the fact that U transpose is the inverse of U, and A inverse satisfies U left multiply or right multiply, they all obtain identity. You immediately know that the row vectors must also be orthogonal vectors. Okay, so let's stop here. Any question?
Is this only true for orthonormal matrices or for any orthogonal matrix?
So as we